Hello, my name is Felipe. I'm a postdoc scholar here at the Department of Plant Pathology, Environmental Microbiology at Penn State. But today I'm here to present a research that I developed during my PhD at The Ohio State University, where Professor Pierce Pohl was my advisor and Professor Larry Madden was my co-advisor, and they are both co-authors in this study. The title of my study is the development of a weather-based models to predict contamination maize grains with deoxynivalenol. If you never heard about gibberella rots or are unfamiliar with the disease, this disease is the most important ear rot disease on Midwest, definitely in Ohio. The disease cycle is pretty simple. The fungus Fusarium graminearis survive in the crop residue over winter, and during the anthesis or silk or R1, infect the silk of the corn where it started the infection, usually in the tip of the ears. At some certain occasions, physical damage on the rusk, usually most frequently caused by insects, can also be a pathway for infection of the ears. But these type of infection are not were not the focus of this study. This study is focused on the infection through the silk channel. The impact of this disease, there's basically three different impacts. It impacts the yield loss, the grain quality, and also the mycotoxin contamination. Mycotoxins are secondary metabolites produced by the fungus who are harmful for human and animals. And they are the most important consequence of this disease. And the most common mycotoxin produced by Fusarium graminearum is deoxynivalenol, also commonly referred as vomitoxin because of cause of vomiting on animals. With the swine here to illustrate as one of the most susceptible animals to this mycotoxin. Well, mycotoxin is an important problem for every single crop that has a fungus who produce this type of a toxin. But maize is a special case, especially here in the West, where a good proportion of our production is used on the ethanol production. And the ethanol production has a subproduct which is called DDGs, which is very important for feed animals as a very important source of energy and protein for animals, a cheap one. However, here in this scheme, we can see that we have for the production of ethanol, we have basically a few inputs. We have the corn, enzymes, and yeast. And we have three primary products, which is CO2, ethanol, and the DDGs, which is used for feed the animals. However, the mycotoxin produced here, input here on the corn, obviously will not be with the CO2 proportion, will not be in the ethanol production, and they will all concentrate here in the DDG proportion that is used to feed animals. But how much is this concentrated? Well, some researchers show that these increases could be up to threefold increase, and this is because about 2/3 of the corn is composed by starch, and this starch is converting CO2 and ethanol. So all the mycotoxin produced in this part is concentrated on the DDGs. So we have a good proportion of our market highly susceptible to mycotoxins, and even a small amount of mycotoxins could be a problem on situations like this. Well, we basically have a few tactics to manage the gibberella rot. We have a cultural practice, chemical control, and host resistance. However, there's some questions if the actually cultural practice actually are doing any effect there at all. Chemical control sometimes not unstable, we don't have consistent results, and the host resistance are not ideal at this point. Most of our hybrids are susceptible, moderate susceptible, and even those that are more resistant is still showing a good amount of mycotoxin under certain types of conditions. With this in mind, our group developed a program, my PhD research developed program, to study and understand better the gibberella rot and how it develops. So we have developed in 4 sections. One to understand the epidemics in Ohio and how the weather is associated with the weather. Another component is how our hybrids are stable, or in other words, if one hybrid is classified as moderate resistant, that hybrid will be moderate resistant in other conditions, in other environmentals, in different years and different locations. Other part is the relationships, how much severity, how much mycotoxins should I expect under certain types of severity, or how much yield will impact how much yield I expect to be impacted by this disease. And finally, we use all these 3 components to develop a risk assessment model, which is the focus of my study here. 3 of these parts are already published, include the one that I'm presenting here today. I have linked these papers here, but you can also find on the plant disease or phytopathology. The specific one is this specific one that I present today is under at this moment as first look at phytopathology. So during the years of 2015 to 2018, in 10 locations across Ohio, we have 15 to 16 hybrids. So we have 1 plot for each location, each hybrid on each location. These locations are the same. The corn performance trials are conducted in Ohio, and they follow the same management. Everything is the same. And for these studies that I present today, everything was a natural infection. So when the corn was ready to harvest, went there in the harvest 5 to 10 years, and we estimated the visual gibberella rot severity, and we send samples to quantify the known contamination in these grains. Well, this disease was usually very sporadic. It didn't happen every year. As a plant pathology student, I was lucky that I have plenty of information during my PhD. And all these pictures, as you can see here, are pictures from epidemics that we have in Ohio during this year. More specifically, those are from 2018. This is actually are not our plots, but they still represent what we have seen. And for the development of a model, risk assessment model, as we have actually perfect years. So for example, for 2015, in our 149 samples, we did not have detectable levels of deoxynivalenol. However, for 2016 and 2018, about 80% of our samples have detectable levels of mycotoxin. And with about 20% of those samples have mycotoxin contamination above 5 ppm, which we consider under these circumstances very high. So during those 4 years, we have 1 year with very low, with no mycotoxin observed, detect on our samples. We have 2 years with a lot of epidemics across Ohio, and 1 year, 2017, as intermediary year. For each location, we have a weather station equipped with a sensor for temperature, surface wetness, rain, and relative humidity. And with those sensors, we generated multiple weather variables. So for example, we have since the simple, like for example, average relative humidity, or we have a conditions, for example, temperature between 15 and 30 Celsius degree, or some more complex with the combination. So for example, this one is temperature between number of hours with temperature between 15 and 30 and relative humidity above 9%. Here's a picture of the weather station that I use. Here's usually before each season, I install all of them in the same field for 2 or 3 weeks to make sure that all of them are calibrated. They are basically talking the same language. Okay, now consider how we use those weather variables across the season. So, for example, consider that a specific field in a specific year, R1 was reached at August 1st. So for this study, we consider 60 days after R1 and 30 days before R1. We consider the weather from this timeline. And we standardize everything based on R1. So we start to say August 2nd, August 3rd. We replace by 1, 2, 3. So we can compare different days. We can compare everything relative to R1. Now take a weather variable like an average temperature. And take, for example, a window of 5-day windows, and you see how many windows we use in the second. What we did, we used the 5 days for the 5 days window in this example, the average of these 5 days, and estimate for example, here for the day 60 after R1 is not 25.1, but actually the average of these 5 days include 60. So instead of 25.1 will be 24. For the next day, we just move our window and calculate again. So in this case, it's not going to be 27, going to be 22.5, and so on for all the possible combination. We consider for this study, which is a separate study, is a Window-Pane analysis. We consider 43 weather variables. We split our 24 hours and 12 hours, consider only the night time from 8 a.m. to 8 p.m. The opposite, from 8 p.m. to 8 a.m. We study 6 different windows, 5, 10, 15, 20, 25, and 30 days. And this combination of these three generated approximately 32,000 summer variables. And what I mean for the summer variables is, for example, here for the example that we just said, the average temperature for 5-day windows for the day 60 will be one variable. For the day 59 will be another variable. And the same thing for the window of 10 days, 15 days, or instead of the temperature, the relative humidity. So you can see how this number of variables can grow really fast. We did the experiment run correlation between these variables and the contamination of the mycotoxin. And this association, this correlation, we estimated 1,000 times through Bootstrap. We use only Deoxynivalenol data, and we consider for this study, specifically for this analysis, only one hybrid that we have as a standard of susceptible. So we did not did this for all the 15 hybrids. We did only for one standard hybrid that we classified as susceptible before this trial started. Now here I have a few results from this study. And as we can see here, the first two charts, they just show that split the day between 24 and 12 hours actually didn't help that much to explain the variation. Here I have just for two variables, but this would be basically in general the same results, where the 9 time is that these dashed lines usually have a weaker correlation or similar correlation. So for our future analysis, we only consider the 24 hours. Here for the different windows from the 5 to 30 days, we can see that short windows like 5 days are very susceptible to extreme weathers, to change the weather. So for example, you have 4 days without rain, and then you have 1 day with heavy rain or something like that. This change very dramatic the weather and these situations. While windows like, for example, 25 or 30, it takes longer time to see any trend on this. And we find the windows between 15 to 20 were more reasonable for based on what we saw in this association. Here's another example that we can see based on multiple different weather variables, as we don't have a single period relative to R1 that give us a strong correlation. So what I mean by that is, if you take, for example, this variable, which is temperature between number of the hours with temperature between 15 and 30 and relative humidity above 90%, we can see that we have strong associations, and this time about 15-21 days after R1, and also we have relatively strong but negative correlation before R1. So we have two important periods, and we can see that this is true for many other weather variables. So for this specific disease, different than the others, we will have to consider, we learned that we have to consider multiple times. Now, the question is how I can use all this study, all this information of association between the weather to estimate actually the risk of having disease, or make decisions such is the risk high enough for a spray of fungicide, or the risk is high enough that I have to change my strategy of harvest. And that's why we develop this risk assessment model. And basically the question that we're looking for is, what's the probability of my grain will be contaminated with a DON equal or more than 1 ppm. And 1 ppm is important here because it's basically a threshold that will limit the use of this product for certain types of you will limit for corn to be used for certain types of product. And it's very conservative and well above the limit of the detection of our tests. So before our analysis, this is everything that we have learned before. For this paper, the risk assessment model, I did not consider the 43 weather variables. Some of those variables we even not consider here. We learned that we don't need to consider the 12 hours, and we choose a 15-day window as a reasonable variable, a reasonable window length. Instead of to consider every single day, we consider only 6 in start day, 6 days relative to R1. We consider the 14 days before R1, 7 days before R1, 7 days after R1, 14 and 21. This combination generated 222 predictors, which is a lot lower than the 32,000 that we have in our analysis before. To not inflate our data, we have, just a reminder, we have 15 to 16 hybrids per location. We actually did the average of mycotoxin for these 15 hybrids, depends on the class, and we classify our hybrids on susceptible, moderate susceptible, and moderate resistant. Now the model itself, we took those 222 predictors, and we did actually a correlation with those 37 weather variables. Consider only the period of R1. So we take the R1, how was for all the 40 fields, how was the weather, and did a correlation with all these 37 weather variables. And we remove those who were extremely high correlated. And from those 37, we ended with only 22 weather variables. And we dropped from the 222 predictors to 132. Our model 1 of our approach was split by start times. Then we used LASSO regression to reduce from the 22 to 15 weather variables per start time. We did also use our subset algorithm to estimate, to see all the possible model combination. And finally, we estimate the performance of those models using cross validations. And we use another strategy that is not split based on the start time in those 7, 14, 21 days after one, for example, but consider all 122 predicted and use LASSO. In the next slides, I will spend some time to explain a little bit about LASSO, our subset, and logistic regression with cross validation. Now, speak about LASSO. LASSO stands for Least Absolute Shrinkage and Select Operator. It's a very popular machine learning method and regression method that could be used to predict something by itself, but also for select predictors. In our case, we use LASSO to select our predictors, and LASSO works in the following way. Like for logistic regression, here we have our likelihood function here, and LASSO applies. Well, here's likelihood function, and LASSO applies a penalty term that we are called lambda to the sum of all the standard coefficients. So what this means? That means that for each coefficient here will be multiplied by this penalty term, which will reduce our maximum likelihood function here. So that means that, for example, for those very small coefficients who actually contribute almost nothing with the model performance, they will be forced to be 0. And here we can see how the coefficient change as we increase our penalty term. Again, this is log scale just to represent. So here we have a lower penalty and here a higher penalty. So you can see how this forces many of coefficients to become 0, because if they do not improve the model performance, they cause more harm than do good. One thing that we can see is that some of models, some of the coefficients, they increase, they change time. This is because LASSO also works very well with data that are correlated. For example, let's say we have 2 predictors who basically are highly correlated. So LASSO will eventually eliminate one of them and the other will have all the weight. So it works by compensating. So for example, here we force our 22 predictors to a different range of lambdas, and we select when we have 15 predictors. So we reduce from 22 to only 15. And here is the predictor select for each start window. So for example, for 21, the surface witness, number of the hours with surface witness above 90% was not selected for the 21 days windows, but was selected for the 14, 7, 0, not for -7 and for 14, and this so on and so forth. So you can see that each window will have a different set of predictors selected based on LASSO. Okay, after we select all our 15 predictors per window, we submitted those predictors to our subset selection. What this algorithm does is basically calculate one logistic regression for each combination of predictors. So for example, temperature, and for a model with two predictors will be temperature and all the other four combination with all the other 14 predictors, or temperature, relative humidity, and all the other 13 combinations. So we basically configured our model to predict from 1 to 5 predictors, build models with 1 to 5 predictors, and this generated thousands of models. So for each combination of window and number of predictors, we selected the top 5 models based on the AIC criteria. So here we have a ROC curve from those 150 models here represented, just to illustrate how was this. So for example, for the window of 21 days, we have the one predictor will have this 5. For 2, we have this 5. It is 150. Based on this ROC curve, we can see that models with one predictor did not perform as well as models with more predictors, and this is, of course, this is expected. However, even though it has only one predictor, you can see that models, for example, for 21 days after 1, performance very relatively well, and with 2 also perform well, and increase the numbers usually do not mean a significant improvement in the ROC curve. Yeah. So after we have those 150 models, logistic models, we use cross-validation to test the performance of this data, of these models. So cross-validation works this way. We have all our data, and we split in our case, it was a 10-fold cross-validation. There is different cross-validation. We just explained the one that we did. We did a 10-fold cross-validation. So that means we split all our data in 10 folds. So, and from these 10 folds, you use part of this to train a model, to build a model, and then another fold to test that model. And this is different than, for example, the traditional way where you build a model with one data set and test it with a different independent data set. This one, for example, here we use the fold number 1 to test and all the others to build the model. So we build our models based on these 9 folders, and when we test here, and we recorded the performance of our model. Then we did the same thing, but now testing with the second fold. So we use all the other 9 folds to build the coefficients and test on the second. Same with the third, and all the other possibles, all the other 10 folds. So we select one fold to test and use the other to build the coefficients. After that, we use all this performance and we do the average, and then we have the cross-validation performance. And that's how we evaluate our models. As we can see here, we have across those, so each point here represents one of those 5 top models from the cross-validation. And we can see that, of course, we have, as we expect, improvement as we add more predictors. But after the 2, we do not have that significant improvement. We also can see that usually the 21 days are under the best models in all the criteria. We have a pretty stable specificity, but the sensitivity, which is the proportion, just go back for a second. Accuracy is the proportion of the cases that our model correct predict. Sensitivity are the proportion of positive cases. In our case, if the contamination by deoxynivalenol was above 1 ppm, and our model correct predict in that way. And specificity is the proportion of negative cases, in our case that deoxynivalenol was below 1 ppm, and our model correct predict that. So our models, independent of the number of predictors, they are pretty good. Depending of the number of predictors in general, independent of the number of the window, with exception close to R1. Our model have a very stable specificity, but sensitivity actually was not that great for some of our windows, especially close to R1 with one predictor. But once again, the 21-day windows. And it's important to emphasize this 21-day windows. It compromises is the period between 7 days after R1 to 21 days after R1. Remember that our windows are 15-day windows. So it compromises is the weather from that period, and that period is the end of pollination, the start of R2, depends of the hybrid, but usually in that period. So for the 150 models, we could, but it's not that very informative to just report those 150 models. So we have to select a few that we consider best, and we use a few criteria. So basically what I just showed, models with 1 or 2 predictors, simple models, are actually pretty good most of the case. Increase the number, the complexity of our models will increase the bias, and that's not something that we want. So we limit it to 1 or 2 predictors. So this reduces it from 150 models to only 60 models. Then we use a balance. Balance is the average between sensitivity and specificity. So here in our case, the balance must be at least 0.75, and this reduces even more from 60 to only 16 models. Some of these models, they have basically the same, a different representation of the same weather variable. Let's say, for example, average temperature and minimum temperature. So they are representation of the temperature. So those models were not included here. Finally, 2 models where even though after they pass all these criteria, they still have a sensitivity very low, below 0.65, and they were not included in what we consider the final 11 models. Here we have our models. I'm not going to over all of them because of the time. You can go and see details in the paper, but I'd just like to bring a few things to your attention. From the 11 models that we select as our final models, only 4 are not from the window of 21 days. That, once again, is the period between 7 and 21 days after R1. Only 2 are before R1, and no model was from R1. So the weather between R1 and 15 days before did not produce any model that was selected here based on our criteria. An interesting thing, as we expect, usually we see after R1 an increase on the relative humidity and warm temperatures are usually associated with a higher probability of have mycotoxin above 0.1 ppm. But kind of surprised for the period before R1 actually increase on the variables associated with moisture actually reduce the risk of have mycotoxin above 1 ppm. Here's a few metrics of the performance of our models. Usually they are relatively very good for this stage of the model, consider comparing with other models of prediction. Once again, specificity was very good, usually above 0.8, with some models, for example, number of the hours with relative humidity above 9% at temperature, above 20 Celsius degree, have a very good specificity, doesn't have that much good sensitivity, and but have a good accuracy. One that have a better sensitivity is average relative humidity and temperature, minimum temperature, and these are both positive coefficients. All this performance, they use the cutoff as 0.5% in the logistic regression. This graph shows there is still room to improve this, but for this study, we prefer do not adjust it for the optimal cutoff. So we use a 0.5% probability to classify as yes or no. Well, I mentioned before the LASSO. We used LASSO for reducing from 22 predictors to only 15. But why not use LASSO to the 132 predictors? Well, that's obviously was possible, and we did here. So we provide for the model, the LASSO, all possible predictors, and basically we submitted to a range of penalty terms, and the strongest penalty when generated only one predictor was the predictor that was selected was temperature between 15 and 30 Celsius and number of hours and relative humidity above 90%. And this generated quite a good model. So here in this plot, here we have the performance of this model. Here we have an example of how was the coefficient changed over time. See how LASSO works here in this plot here as the predictors that was selected based on different penalty weight. As we can see here, we have when we select only this single predictor here, we have a pretty good performance, and of course, as we expect, it improves as we add more predictors, but it not improve that much. So, for example, take this one here has 22 predictors, and there is not a model with 22 predictors and not that much improvement compared to one that is only one. Okay, this was supposed to be a short video, but it's been almost 40 minutes, so but I have a few take-home message. One very interesting thing was use LASSO regression to select predictors, and was very useful to analogy or work was one among the first to use these. Shah also using the similar, but he used it in he used in similar way, but for assembly models. In general, warm temperatures and high moisture between 7 to 21 days after one what most produce the most predictive models for quantify the risk of have-done contamination above 1 ppm. And this is a first study. This study is being continued by well-qualified people in Ohio and other places. And these are important steps to develop a predictive model, decision tool for farmers and stakeholders for mitigate the effects of mycotoxin on maize. I have to thank you, of course, the amazing people of Cereal Pathology Lab in the Ohio State University, my advisor, Professor Pierce Paul, for all of his mentorship during my PhD, as the same as my co-advisor, Professor Larry Madden, and the people from HCS who run the corn performance trial, Rich Minion, and now Professor retired, Professor Peter Thompson, and the farmers who welcomed me during the time that I was conducting research in the farmer. I also want to thank the sponsor of this project, which is the Corn and Wheat Board of Ohio, USDA, and Biocrop Science. And a special thanks also to my current lab, to ISCAR lab, who helped me very well since November 2020. Okay, if you watch this video till now, thank you so much for doing so. If you have any questions, you can contact me. I know that we'll have a time during the Plant Health 2021 that I'll be there to answer questions, but if you do have more questions, you can contact me by my mail. You can find me on Twitter as well. You can also read this paper from these studies already published. There is other models that I did not include in this presentation. So for example, the relationship between some cultural practice like the previous crop, the tillage, on the risk of have mycotoxin above 1 ppm, how good is the severity to predict the risk of the mycotoxin be above 1 ppm, or the incidence, not the incidence, the presence or not of symptoms. All this information you can read on the paper that is already available, still as a first look, not formatted, but will be formatted, I believe, very soon. But you can also contact me. Thanks so much again for watching, and I hope you enjoy the conference. Bye.